Hello, welcome to Quantum Projects, where analytical calculus is pretty much useless. In today's video, I'll teach you everything you need to know about numerical integration. By the end of this video, you'll be able to explain to your friends what a Runge-Kutta fourth-order numerical integrator is, how it works, why it exists, and why it's important. Why would you ever need to be able to do that? I don't know. To answer that, let's do a quick recap on integrals themselves. An integral is, in essence, a mathematical operation to determine the area under the curve of a given function, f of x, on a given interval. There are two types of integrals, indefinite and definite. Indefinite integrals yield the antiderivative of f of x. Let's call it g of x, which has some interesting properties. Definite integrals take that function, g of x, and evaluate it at two separate points, a and b. According to the fundamental theorem of calculus, g of b minus g of a yields the area under the curve of f of x on the interval a, b. Both definite and indefinite integrals involve taking an integral of f of x, which can be challenging. If you've taken a calculus class, I'm sure you know what I mean. But what you may not know is that taking the integral can sometimes be completely impossible. For example, the integral of sine of e to the negative x is not well defined using elementary functions. Because no corresponding g of x exists for this f of x, indefinite integrals are basically out of the question. But what if we wish to take a definite integral? Over the years, mathematicians have developed several algorithms for estimating the area under the curve of such functions without taking an integral at all. This is numerical integration. The name of the game for numerical integration is knowing where g of x goes by knowing what the slope of g of x is at any given value of x. Remember, g of x is the antiderivative of f of x, making f of x the derivative of g of x. The definition of a derivative is a function describing the slope of the function that it is the derivative of. In other words, at a given value x, the value of f of x is the slope of g of x. We may not know g of x, but if we know what the slope of g of x is at any given point in time, we can estimate where it's going. That's all a bit confusing, so let's work through a basic example using... Let's say f of x equals 2x. Therefore, the slope of g of x at any given value of x can be described by the function 2x. Let's assume our mystery function g of x starts at 0. F of 0 equals 2 times 0 equals 0, meaning the slope of g of x at 0 is 0. Let's draw a line of slope 0 until we reach x equals 1/2 and check again. F of 1/2 is 2 times 1/2 equals 1, meaning the slope is now 1. Let's draw a line of slope 1 until we reach x equals 1. F of 1 is 2, so now we draw a line of slope 2, etc., etc., etc. If we continue this for a while and then plot the actual integral of 2x, which is x squared, we'll see that the curves kind of match, and we didn't even take an integral at all. But there's a problem. As time goes on, the real curve strays further and further away from the original one. This is called error, and it's bad. So how can we fix it? We can reduce the time steps, sure, but that only slows down the problem slightly. We need a more accurate way to predict the slope between calculations. Let's try something a bit fancier. We'll again work with f of x equals 2x, but this time, instead of assuming that the slope of g between 0 and 1/2 is just the slope of g at 0, we'll find the average slope between 0 and 1/2 and use that instead. We'll do this by computing four slopes, namely k1 through k4. k1 is equal to the slope at 0. F of 0 is 0. k2 is equal to the slope halfway between 0 and 1/2. So k2 equals f of 1/4 equals 1/2. For the purposes of this video, k3 is equal to k2. Finally, k4 is the slope at 1/2, the end of our interval. F of 1/2 equals 1. We will now take a weighted average of those constants to obtain an average slope. This slope is equal to 1/6 times k1 plus 2k2 plus 2k3 plus k4 equals 1/2. If we continue this, we'll construct a guess curve just like we did before. However, as you can see, error accumulates much slower, and we haven't even changed the time step. Magic. In fact, if we reduce the time step even further, we can very accurately calculate g of x without having any idea of what it actually is. So we've already discussed that numerical integration can solve integrals that analytical calculus simply can't solve. But why do we care? To demonstrate why numerical integration is useful, I'm going to introduce you to a problem that you may have seen in your senior year physics class. We're going to calculate the time it takes for a ball to strike the ground when dropped from a height of 20 meters. But we're going to do something that your physics professor never would have dreamed of doing. We are going to add air resistance First, let's derive an equation of motion. The foundation, I'll let you guess. Is it A, Newton's second law, F equals ma? B, Newton's second law, F equals ma? C, Newton's second law. Let's draw a free body diagram of our ball. We have two forces, gravity, where F equals mg, and drag, where F can be modeled using Bernoulli's equation of drag in incompressible flow. F equals 1/2 rho x dot squared times c, where c is the coefficient of drag times the object's frontal area, and x dot is the time derivative of position, velocity. Let's sum the forces and set them equal to the mass of our object times acceleration. The net force is just 1/2 rho x dot squared c minus mg equals mx double dot. Let's simplify this to have x double dot on one side. Rho c over 2m x dot squared minus g equals x double dot. Uh-oh, we have a nonlinear differential equation, and it's second order? What do we do? Well, step one is to prank the equation by turning it into a system of two first-order equations. So to do that, we're going to create two fake variables. A1, which is equal to x, and A2, which is equal to x dot. Now we can rewrite the equation as two first-order equations. Equation 1, A dot equals A2, and equation 2, A2 dot equals rho c over 2m A2 squared minus g. In step 2, we're gonna, what was step 2? It's probably something important. It's probably got to do with this entire video's topic. We used numerical integration. After all, we now have formulas describing the slope of A1 and A2 everywhere, which is all we need to numerically integrate their solutions. Let's use MATLAB's ODE45 function to do it, a numerical integrator using the Runge-Kutta fourth order method. And there you go. If we give the ball these parameters, we're going to hit the ground in about 2.22 seconds at a speed of 15 meters a second. In today's video, we've defined numerical integration, learned about two ways to perform it, and applied it to a practical problem. If you'd like to check out any of the codes, they'll be available for free in the description of this video. Thanks so much for watching. See you later.